Today we're going to finish the acoustics and pipes, that subject. Right, and then tomorrow's lecture is on acoustics and cavities for the lab. And then Monday's a discussion on acoustics and pipes. Okay, we're now finally we're at the point of and you'll see, we're at the point of dealing with the, being more realistic about the driver, to deal with the combined system of the driver and a pipe. And if you, as we go through this, you're going to find that this is really drawing on a lot of material from this quarter and last quarter. So it's an appropriate place to end, I think, here, as you'll see. So here's the obvious standard model of a driver, a damped simple harmonic oscillator. So the driver will have some stiffness, some inertia, and some damping. And there's an external force here that's exerted on the mass. And as I've told you before, this is a subject of an entire course here, the transducers course, right? So we'll spend a lot of time on this in the future. So right now we just deal with this little f of t, which is going to be this oscillatory force on this mass here. Now we're going, for simplicity, we're going to consider, because we have dissipation, weak dissipation, and weak incidentally means this here. The absorption coefficient times the length of the pipe is much less than 1. Because we have the weak absorption here, we now have a realistic model. We have dissipation. We also have dissipation here too, incidentally. But because of that, we're just going to take the simplest case now of a rigid termination there, rather than deal with some other, we're going to take the simplest impedance here, terminating impedance. And we'll see that that's complicated enough. So you remember that this external agent here that's driving this the mass back and forth is going to, we're missing a lot of people. Something happened? Mudslide?
Weather.
No, not here. We don't worry about mudslides here. Southern California. The weather, yeah, I don't know. So this external agent here sees or feels an impedance that's driving this mass back and forth. An impedance is the force, complex force divided by the complex velocity, right? Now that impedance has to be, and I think you'll all buy this now, we've been through this before, especially from what you did in 3119. The impedance is going to be the sum of the two impedances of these two parts of the system here. And the reason that happens, and I'm just reminding you of this, is that we're dealing with a force divided by the velocity. You have the complex force divided by the complex velocity. And this is, of course, at the input point right here, x equals 0. That's the impedance here. And the total force, there's a force here exerted by the driver, right? And then there's a force due to the fluid. And those two forces add. There's a velocity here. There's a velocity of this point. There's also a velocity of the fluid, but they have to be the same. So that's a short version of why the impedance here is the sum of these two impedances, because the forces add and the velocities are the same. Now, I realized when I was thinking about this last night that That doesn't really prove it. You have to look a little bit deeper. But I think it's a true statement. It's just that it's intended to just jog your memory, to make you, to remember that the total impedance is the sum of these individual impedance. Impedance seen by this drive is going to be the sum. You can prove it, and that can be done. That's in the book. It's actually in the book in this section here. And it's basically you use Newton's second law. You apply Newton's second law to this mass. And then you beat on it, and eventually you can cast it in this very simple form. And this is the main reason people use impedance, or at least one of the reasons. You can beat this Newton's second law into this very simple form here. That the impedance seen by the drive, which by definition is this, right, at the input point here, is the sum of the two impedances, where the driver impedance, as you know, for a mass on a damp harmonic oscillator, this is going to be the impedance with the mechanical resistance, being the real part, and the reactance being this combination. You remember this from 3119, we've dealt with it here too, in this class. That impedance plus the impedance of the tube, and the impedance of the tube, which we derived, I guess, yesterday, for weak absorption is given by this, not an obvious expression. And remember, and one of the reasons is because it has resonance and anti-resonance in there. It has that information in here. But again, so this is just Newton's second law, and you say, well, why don't we just write down Newton's second law? Well, you do it. You'll see. It's like a lot of effort. You can look in the book, like I said. To derive this, in this case, it takes some effort from Newton's second law. So that's one of the reasons people use impedance. They can just write this down. You just have to realize that the driver is going to see the sum of the two impedances. The external agent that's driving the system is going to see the sum of the two impedances. Okay. Now, so if we just had the driver, we had no pipe, okay, resonance is going to occur, and this is from 3119, where the reactance is equal to 0 of the driver, and it's just going to be the usual square root of the stiffness divided by the inertia. Okay, so that's where the driver alone resonates. The pipe, we discussed this yesterday. The pipe resonates and anti-resonates when the imaginary part, when this is equal to 0, right? And we get this doubling of zeros here because of the product, and that half of them. What we typically call a resonance, those resonances are interleaved with the anti-resonances. The problem before us right now is what happens when we have the combined system. And it's obviously different. Here's our condition for resonance. The total reactance has to be 0. It is, now that I think about it, I guess this is a sufficient condition. If you assume this and this, if you assume that their individual reactances are 0, then this will be true. But you're going to hit a problem there. It's going to be inconsistent. It's not going to work. It has to be. We've got to look at this. We've got to look at the complete system, the combined system. Okay, so when we do that, I look at the imaginary part of this plus the imaginary part of this has to be equal to 0. This is what we get. Now this is a complicated expression. You want to notice here we really have one variable. It's the frequency, or what's convenient here, because it's in the argument of these sinusoids here, is KL. So KL is a dimensionless quantity, obviously, and that's what we're going to treat as our variable, our independent variable. So we'll be, in the language of acoustics, we'll be sweeping in KL, which is essentially the same, because omega is equal to CK. Right? It's essentially the same as sweeping frequency. So that's the first thing you want to see here. There's really just one variable. We see omega and KL, and we'll deal with KL. The next thing you want to see is that there are a lot of parameters here. We got now, all of a sudden, we've got the mass of the piston, we got the stiffness, of the driver, the density of the fluid, the speed of sound in the fluid, the cross-sectional area, the absorption coefficient, the length of the pipe. So, how do we handle that? Well, there's an indication how it's handled right here. As you'll notice that L, you see L in two places here as part of the independent variable, which we just think of as one quantity here, right? KL. And then you'll see that but aside from that, the only place it occurs is it's multiplied by the absorption coefficient here. And that's the only place the absorption coefficient appears too. So that reduces, instead of having to deal independently with these two parameters, alpha and L, there's really just one there. And you'll notice that that's dimensionless, right? And that's really the key here. And this is what people do all the time, especially in research. You've got some usually pretty complicated system. There can be a lot of parameters. You want to beat it down to the essential number of parameters. And how do you do that? You look for dimensionless quantities. You guys I hope you've been through this, but it's indispensable in research. You don't want to have to go through and start changing independently all these quantities to get where you want to go to. There's too many of them. So you look for the essential number. And you do that by looking at dimensionless quantities. So let me show you how it works here. It's a natural guess that just the mass alone of the piston, is not going to be important. In other words, here's another way of saying it. What's a small mass of the piston? What's a large mass of the piston? Anybody? We don't know, right? And the reason we don't know is we need to compare it to something. Whether this is small or large, it's going to be relative to something else. Well, there's only one other mass in town. What is it? There's mass in here, right? So it's very natural to look at a parameter, which is the ratio of the masses. So here we're going to call it, following the textbook, we'll call it little a. M is the mass of the piston. The mass of the fluid is just I should probably invert this, is the mass per unit volume times the volume. And in equilibrium, the mass is not going to change, but we can evaluate it in equilibrium. We just take the ambient length. The length is changing, but we take the ambient length, L, multiply by the cross-sectional area. That's the volume, ambient volume of the fluid, multiply by the density, that gives us the fluid mass. So it just has to be that this is going to be the relevant quantity in regard to mass. And in the end, we'll prove it. But it just really has to be, because there's no other masses. Okay, what about the stiffness? What do we mean by large or small stiffness? What do we compare the stiffness to? Well, again, the fluid has stiffness. If you remove the driver, just have this piston here. If you push on this, you're going to feel a restoring force. Or if you pull it back from equilibrium. Okay, it acts like a spring. Now, I don't think we've talked about that before in this class. So what we're going to do right now is find the spring constant. This has a spring constant. This acts like a spring. Now, first thing I need to tell you is the fact that it behaves like a spring is that it's only going to behave like a spring for small displacements. If you go to bigger displacements, you'll see nonlinearity. Okay? And all we care about, this is a linear course, so we're just going to look at small displacements. So let's go through that calculation. It's a simple calculation. I don't think you guys have seen it before. So the fluid, we can just call this capital M. That's all we need right now. That's the mass of the fluid, which is constant, right? Let's call C the displacement of the piston from this means from equilibrium, right? Okay, so we want to consider, now, we want to find the stiffness of the fluid. Inherent in there is that we want it to, that's quasi-static. If we start going at higher and higher frequency, acoustics is going to be involved. It's not going to be a simple Hooke's law thing. It's going to be complicated. That's what we're trying to solve, right? So right now, to compare the stiffness of the driver to the stiffness of the fluid, we're going to look at the quasi-static stiffness of the fluid. And we want to do that, of course, adiabatically, because that's what's relevant for us. Everything that's happening here, acoustics is adiabatic. So we're looking at the low frequency response. This is the relationship between the pressure and the density in general for acoustics. You've seen this before, right? This is the acoustic pressure. The change in pressure is c squared times the change in density. All right? So let's put in what the density is. When there's some displacement, when the piston is pushed in, the density goes up. The density is going to be the total mass divided by the volume, and here's the volume. So this checks out when we're calling positive c going this way. When c is positive, the length is reduced, the density is going to go up, right? Here's the equilibrium density. All right? And you can see here that in terms of the variable c, this is going to be a nonlinear. The p and c are related nonlinearly here, right? However, we're only interested in small displacements. So, first let me factor out an m and an s. What happened? Looks like the s is missing, huh?
You brought it to the other side.
Oh, right. And why did I do that? Because what's relevant for a pipe? Force, not pressure. That's where we're headed, right? And we're Hooke's law, force is proportional to the displacement. So I brought that over there, thank you. I factored out an m. And now we do our thing that we've done many times. Because c is a small quantity, I'm going to first go dimensionless here just to be clean about this. And then I should have had an approximation. I'm going to put a dot above there because 1 over 1 minus a small quantity is approximately 1 plus a small quantity, something we've seen many times in this class. And then I multiply through back by the L and I get this. When I take this and substitute it in here, this term's going to cancel with that. And we end up with the force. Here's the force. Here's the displacement. What's all this stuff?
Spring constant.
That's the spring constant, okay? So because we have so much notation here, we're not going to call it anything. I'm just going to leave it like this, okay? That's the spring constant for a column of fluid. And that's entirely general as long as the displacements are small and as long as you do it adiabatically. Where is the adiabatic information in the stiffness there? Do you see it? Where's the information that it's adiabatic? It's C. C is how the pressure changes with density adiabatically. If we're isothermal, we could still use this C, but it would have to be the isothermal speed of sound. The Newtonian speed of sound. Okay, so this is the stiffness of the fluid. So a natural dimensionless variable. And it really has to be, there's nothing else around. It's natural to form this parameter here as the stiffness of the driver divided by the stiffness of the fluid. Now, now what do we do? Well, we now go back to our expression that we want to deal with here. And first of all, let's get rid of omega. We're going to write it. We're going to write it like this. I'm going to, okay. So, let's see, how am I, I'm going to write, oh, this is actually kind of interesting. I'm going to replace omega with CKL over L, which looks stupid, right? But it's not, because I know I want to head towards this. That's going to be our natural dimensionless variable. And this L, we just got to work with it. And I'll let you do this. And it's kind of interesting. But if you beat on this and form these quantities in there, you know, multiply and divide, like, what am I doing here? I'm multiplying and dividing by L, right? So that I can form this one quantity. You can do that with other quantities, and you want to head towards the dimensionless A and B parameters. And when you do that, so yeah, I suggest that everyone does this, because you may not have much experience with this, and it's a very useful thing. And it's non-trivial in this case. Here's what you get when you do that. Here's what you get. Right. Now you'll notice we actually talked, I wasn't going to, we're just going to, we think of this as one, this is the only place, this is just one parameter, alpha L. It's dimensionless, so we just leave that like it is. So that forms one of our parameters in our list here. And our list is now much shortened from before. We've got A and B and alpha L, that's it. So we've beaten it down. We've roughly halved the number of parameters here by going to dimensionless parameters. So now we've beaten it down to the essential parameters that we would, and we're interested, of course, in looking at the behavior or different values of those parameters. So it's a very useful thing to reduce the number of parameters down to the essential number. In this case, it's 3. Okay, so how do we solve this? Well, the answer to that question is easy. You cannot solve this. No one has and no one ever will be able to solve this, because mathematicians have shown that when you have a transcendental equation involving, in this case, sinusoids and algebraically just, this KL here and 1 over KL, there's no analytical solution. It's impossible to come up. It's kind of a big statement, but you can try. And you can start off with real simple things, solve this. Well, okay, x equals 0 is a solution, right? But there's going to be, okay, maybe this is not good. How about cosine? Pardon me?
No, just the x minus 1 over x. Because then you'd be dividing by 0.
I'm not following you. Okay. So anyway, well, I don't know. There's, if you want to consider this, and this is appropriate for what we're going to do, if I'm looking for solutions like that, the natural thing I would do is I'd think of this function. This function looks like this, right? And what does this look like? Well, it looks like this. Right? So this is a very useful approach. This tells me that there's going to be one solution here. It's going to have a solution. And you can, once you try to find it, okay, and you quickly realize that you can't do it analytically. You can do it approximately on a calculator, though, and that was actually done in 31. You did some problems like this in 3119. Do you remember those? They're actually kind of fun, where you hunt on your calculator. You just zoom in, and usually pretty quickly you can get accuracy to 3 significant figures, something like that. You guys remember doing that in 31? I don't think we've done it in this class. I don't remember doing it in here, but it's standard in 3119. Well, we're going to do the same thing. We're going to set this up in a similar way here. And just for the future, for those of you who get involved in this and research, I remember this happened to me. You don't want to just run to a computer. When you're solving a transcendental equation like this, you can throw it into a computer. What you can do is you can bring this term over here, and now you have a function of KL for some fixed parameters equals 0. Then you can use a root finder routine. The problem is that there could be many solutions, and some of the solutions you may not be interested in. They may be unphysical for you or something like that. So the geometrical approach is really good, just at least for a qualitative appreciation of what's going on. Okay, so let's call this g of KL. Let's call this function h of KL. And we do the same ideas that we're discussing here. And here's what happens. Now, following the textbook here, we're going to do two somewhat special cases, okay? The first case here is what they call a light flexible driver. So it means a light flexible driver means that in some sense, and what sense? It's in the math of our problem here. This is small in some sense. Well, we already kind of know what that has to mean. This is small compared to the fluid mass here. However, I need to warn you, we're looking at a pretty complicated problem here. And what you mean by that ratio being small is not obvious, okay? Usually we think, oh, much less than 1. Well, that's not really nailing it down much, right? So we'll see in the graphs here, you'll get a feeling for what we mean by small. So a light driver means that mass is in some sense small compared to the fluid mass in here. A light flexible driver. What does flexible mean? Well, it means that the stiffness is not large in some sense compared to the stiffness in the fluid. Okay? So that's the first case here, just to get a feeling for what's going on. That's this one right here. We'll look at these graphs later on. So here's I've forgotten which is G and H. Yeah, so here's G. Here's the function G, the driver. This, which we've seen kind of this before, this is the function H involving the pipe, okay? Now you'll notice here that this is not going to infinity, and that's because we have alpha is not equal to 0. Unfortunately, they don't give us the value of alpha, or alpha L. They should really specify alpha L. And I don't, if anybody sees it, it's not in the caption. That's where it should be, right? They give these other numbers. They give the A and the dimensionless A and B, okay? And this is kind of interesting, so you'll note that the complexity here. Just jumping ahead for the moment. A heavy stiff driver, heavy, A equals 1/4. Would that seem heavy to you? Remember what A is? It's the piston mass divided by the fluid mass. I wouldn't think that that would be a heavy mass, but it is, all right? So it's just because this is not very simple, it's not simple here. They need to be aware of things like that, not to be naive. Okay, so getting back to here's the light flexible driver. Here's the driver function. Here's the pipe function. And now, what are the solutions? What are remember, we're looking for resonances here, right? Right. Remember, going way back here, this is the resonance condition, the reactance vanishing. That's what we're after here. So what do you see? We've seen something very similar yesterday, right? The intersection points here are going to correspond to resonances. This is going to be a normal type resonance. This is going to be an anti-resonance, just like we talked about yesterday. In fact, now that we're doing this, yesterday with this, I guess it was yesterday. It was so long ago I can't remember. But yesterday we essentially had this massless piston, no mass, no stiffness, no damping. That's essentially a 0. The curve here becomes essentially 0. And you can notice here that for our light flexible driver, it effectively is almost right at 0, isn't it? We have this divergence here, but this doesn't play a role. It's important when it gets to here, and it's close to 0. So that's what we mean by a light flexible driver. We mean that the driver curve is not that far from the 0 line. Okay, let me make sure I'm not missing something here. All right. So if we look at the resonances, you'll see that approximately the resonances are at half integral multiples of pi, right? You can see that this is roughly halfway. This one's significantly off, but you know, if you make the driver lighter or more flexible, this curve will hug the zero more closely, and this is going to come over here. In fact, you can see that the resonances are exactly half integral when we have the zero line here. Okay, now what that corresponds to, I want to make sure one sees this because it's a useful way of looking at this. We went over this before, but sometimes it doesn't stick. When we look at those half integral multiples of pi, here's what we get. So you can see these are half integral. And they correspond, this corresponds to an open closed pipe. All right? So, and this is what we very early in this chapter, we encountered this. We encountered the fact, our math led us to this conclusion that when we had no mass here, and no stiffness and no inertia, that this was acting like an open end. And you think, well, that's not right, and you have the data to prove it, right? In the first experiment, it wasn't, it's an pressure, it's like a rigid, it's like this, okay? So this is clearly a closed end. We're going to get a pressure antinode, but we were getting a pressure node here, which is surprising. Well, it comes about because of the fact that we have this very light driver, and we're seeing it here. We're seeing it here because these mixed boundary conditions here, the half integral multiples, pi, correspond. You can plug in with the wavelengths here, or you can look at the drawing I did in the notes. It corresponds to an open end. The driver end is an open end. No driver, you can think of it as kind of like no driver. A massless driver with no stiffness and no inertia is kind of like no driver, and it corresponds to an open end. Now, those are the resonances. What about there are also anti-resonances here. And you can see that they correspond to approximately integral. That's where the intersections here, they correspond to integral values of pi. And this is where the response must be small. Okay, we'll explicitly see this later on in these other graphs here. All right, so next, I think, let's look at the second case now. So here's the heavy stiff driver. All right, and I'll tell you right now, this is characteristic of, I've never plugged the numbers in. I've always wanted to go back to experiment 1 and check our theory here against experiment 1. And the problem is, and you know, I tell students, if you're interested, you know, let's do it. I'd love to do it. The problem is everyone is so burnt out at this point that nobody's just the last thing they want to do is go back to the first experiment and reanalyze the data compared to our theory. But it would be interesting to do. But presumably what we must find is that it is indeed a heavy stiff driver, because you found approximately a pressure antinode at the driving point, right? Remember that? It was clear. So that's this case. This is an example of a heavy stiff driver. And now it's different. You know, at first it doesn't look all that different. Well, you know, this is lower now, and this is higher, and the intersections are going to change. But it's actually fundamentally different. You have to look at it a little bit. So let me guide you through this. First of all, the resonances here, if you look at somewhat low Ka, you'll see here the resonance and the anti-resonance are really close, right? See, there's two intersections there. You can't, it's out beyond the resolution of here, but there's actually 2 intersections there. The one on this side is resonance, the other one's anti-resonance. All right, you'll notice this is occurring around an integral, and here too, approximately integral values. So for low Ka values, the resonances occur at approximately integral values of pi. At high Ka values, and I wish they'd gone a little bit more here, maybe 7 pi, you can see that the proper resonance here is also approximately an integral number. See, it's close to 5 pi, that intersection right there. But if you look in between, look at this. That's a half integral value, pi. So what we're seeing here is this is the influence of the driver. Okay, so let's explore that. Let me see what's next here. So let me point out something here. So down here and up here, our resonances approximately correspond to an integral. KL is an integral value of pi. And that corresponds to the case of a closed pipe, where you have a pressure antinode at either end, which is what you saw in the experiment. Okay? Now, it's not going to be that it'll be clear later on when we look at the second set of figures here. When we look at these right here, it'll become very clear. Right now, it's not really clear, but I just want to point out to you that what's happened here is that we've got a proper resonance, not an anti-resonance. We're thinking of the proper resonances here. The integral number of pi's here, an integral number of pi's here. There's one that's been inserted in here. There's an extra resonance. If you just, well, I guess we can do it this way. 1, 2, 3, 4, 5, right? We can see we have approximate resonances at an integral number of pi's. If that held up in this region, we should have 5 resonances. How many do we have? 1, 2, 3, 4, 5. We have 6. There is an additional resonance. Is that surprising to you? Because we got this harmonic oscillator that's going to resonate, okay? We didn't really see it before because it was a light, flexible driver. But it's not surprising at all that we have this extra resonance in here. And here it is. Here's where it corresponds right here to this intersection right there. And there's something very remarkable about this intersection. It took me a few years to appreciate this. And let me explain that. But let me make sure I'm not, first of all, missing something here. Oh, wait, I can keep this up here. And just look here. Okay, so compared to the closed resonances, we have an additional resonance, which again is not surprising. Because we have this, we've thrown this oscillator into the system, right, the driver. And I want to show you something interesting here. The solution corresponds to the intersection of these two curves, right? But that intersection corresponds closely to 0 here. And I don't think KFCS point this out, but that is unusual. We've got 3 curves here, and they're all intersecting at approximately 1 point. I'm counting this as a curve, the axis. That's unusual, right? If I have 3 curves, usually, if there's any intersections, they're going to be in pairs, you know. But to have them all 3 intersect is peculiar, and it's an indication that something's going on here. Here's what's going on. If I have a heavy, stiff driver, it should swamp the acoustic system, right? So what do I mean by that? Well, if we look at the resonance of the driver, in a vacuum, the driver is going to resonate where the square root of at a frequency given by the angular frequency given by the square root of the stiffness divided by the inertia, right? How would you expect that to change when you hook up the pipe for a heavy, stiff driver? Well, it should be a small perturbation. So, in a vacuum, we don't have, these curves are gone, we just have this curve. Resonance, of course, resonance corresponds to the intersection of this curve with the 0 line. That's going to give us the square root of S over M, right? So the reason that all these three curves here intersect at a point is we're in this limit, we're in the quasi-limit of a heavy, stiff driver, and it's resonating. The resonance of the system corresponds approximately to the resonance when it's in a vacuum, because it's a heavy stiff. So it makes complete sense. There's physics there. There's physics in this intersection of 3 curves here. It all makes sense. Now, it's important to try to make sense of this because this, you know, this is not a simple theory. This quantitative, I mean, just look at that. This is not simple. Okay, so when you're hit by something like this, you always want to try to squeeze out some, you know, check it. You're doing a combination of checking the results by looking at things physically, seeing if they're reasonable. But you're also getting a feel for what's going on. Okay, so now, so we've struggled through this. I think, you know, it's important to see this the first time through. I think KFCS did this right. It's important to see this. Oh, incidentally, I don't think I told you it's in the notes. This is a mistake. Just to give you an idea of the complication here, this should be the h function, that complicated h function. It's not the tangent, okay? This is the g function we talked about. This should be the h function here. All that mess that we saw before. So that's a mistake. They made another mistake here that I'll point out. And I should, you know, this is not simple stuff when you see mistakes like this. I'll point out the other mistake in a moment. So there's a better way. This illustrates, you know, how we plod through and how we get solutions. But we can have a better perspective on the system once we've been through this. And that is the standard thing that's done experimentally, and it's a natural thing to think of theoretically, is let's look at the pressure. You know, at the simplest point of the system here, the acoustics, the pipe, it's the pressure at the end here. Where there's going to be a pressure antinode because it's a hard termination. So let's look at the pressure there as a function of KL. Let's sweep, and you could actually do this experimentally. So you did this, but you didn't end up with any plots in the first experiment, right? I know, no one wants to think about the first experiment. I understand, believe me. I'm burnt out too. But you could have plotted, you could have done a plot of the, anybody interested? We'll get Jay to set it up. I think that's the answer to the problem. Jay, you should have Jay do this, right? He'll complain. But it is interesting, you know. We're ending up with something at the end of the course here that we could have only done at the end of the course because we're tying together all these things from this course and the previous course. But we had this simple experiment. Well, we thought it was simple. At the beginning of the quarter, it'd be natural to apply this to the first experiment. So one thing you could do here is you could, with a pressure microphone here, which is where you had it in the first experiment, just sweep frequencies and just plot it. So let's do that, but we're going to do it analytically. So we need to determine what that pressure is. So let me show you how we can do that. We previously, if you look back in the notes, oh, I guess it was just, yeah, it was yesterday. We found that the pressure in the tube, this is a slight variation of what's written down there, but you'll see that it can be written like this. Here's the spatial, the sinusoidal. This is the standing wave that's got a pressure antinode at x equals L. All right, you know that has to be true. And it's sinusoidal. You know it's going to be sinusoidal. What's this stuff? Why is that there? Well, that's simply there such that at x equals 0, you get this. You get the pressure, the x equals 0 pressure. So this is actually simple of what we did yesterday. We had that A coefficient yesterday that we solved for. So we did essentially the same thing yesterday. But for us right now, it's appropriate to write it like this. Can you guess why we want to write it like that? Why is this quantity important? It's a race. Impedance, right? If you multiply this by S, it's the force. Yeah, okay. So what we're going to do here is looking at the end, we set x equals to L, obviously. That's going to make this just equal to 1. Okay, and now, what's the pressure? This pressure at the input point. I know that in terms of the input impedance of the pipe, I know that the force divided by the velocity is going to be the input impedance. Okay, and we know this. This is why people use impedance, right? We know this. So we can get rid of this P in terms of U. How do we get U? Well, now we look at the entire combined system, what the external agent sees. its force divided by the entire impedance has to be the velocity, as we mentioned early on. So you put these things into there, beat on it, and I've confirmed this. It does take some algebra, but here's what you get. You get the pressure at the end of the pipe. Here I'm going to use proper notation. So this is the pressure amplitude at the end of at the termination of the pipe. It looks like this. Okay, and now let's see what this looks. Oh, wrong. I guess wrong. No, right way. So here's what it looks like. Here is the light flexible driver, and we get these beautiful curves. You cannot trust these curves, and I'll point that out to you in a minute. Okay. But they're going to look at least qualitatively like this. So here we very clearly see, they call this the antinodal, the pressure at the end, it's an antinode at the end, so this is going to be the pressure then. We get these beautiful resonances here, right? And I keep thinking about the first experiment. It'd be nice to see this. We didn't do this, right? It's not done in the... So here we go. And you can see here that for the light flexible driver, it approximately corresponds to an open closed pipe. You know, we get these, the pressure nodes, the resonances are occurring at half integral values of pi, which correspond to an open closed pipe. Okay, that's the light flexible driver, which is not typical. The typical case of a heavy, stiff driver is here. And you see a world of difference between these two, right? So the first thing, we've talked about this, open, closed, all right, okay. Here, again, similar to what we did before, at low Ka, we're getting now closed pipe resonances, corresponding to what you saw in the experiment, okay? And it happens up here, although if they've gone a little, it would look better if they've gone at least to 7 pi. Okay, we're seeing integral multiples of pi for KL, which corresponds to a closed pipe. And then now you clearly see the insertion of this additional resonance. I mean, it's unmistakable here. There it is, right? If you think of these as the approximation of integral values is starting to break down here, and starting to break down as you come this way and as you come this way. They're getting pushed this way, and they're being pushed because of that additional resonance, isn't there? You can think of it that way. And this is going to correspond to that triple point. That was the word I was using. It's borrowed from thermodynamics. There's this triple point here where we have, for a light strip, in the case of the light flexible driver, where there's, oops, excuse me. Wrong statement. In the case of the heavy stiff driver, it's like the air is not there. That's why we're seeing this triple point, as we discussed. So that's this resonance. You can see they all have the same KL base. So if you just look down here, follow it down, you'll see it's equal to there. Now there's something else that's very important that's happening here, and it's again physically obvious, but do you see it? Look at the relative amplitudes here. You know, the quality factors going down here, which is perhaps not surprising. Again, we'd have to specify the alpha to appreciate why this is happening. This is not surprising at higher frequencies. What's happening here? Do you see it? Look at the amplitudes. It's obvious, right? There's a peak. There's an overall peak. And we're getting the greatest. It's due to the driver resonance. It's physically obvious. That has to happen. But we're seeing it quantitatively here. And we had to go through a lot of work to see it quantitatively. 2 quarters. You can think of this as, you know, the result of 2 quarters of work, right? Okay. Now, there is a mistake here. So I've probably mentioned this before, but you know, KFCS, the first edition of KFCS was a long time ago. None of you were born. I think it was actually did we talk about this? Late 50s? Did we ever you know, that information's out there, obviously. But it was a long time ago, okay? And then our edition is 2000, right? And K, F, and C and S were all getting kind of old. So 2 of them were dead by then. The other ones were getting old. One of them's still alive. Well, we never see him anymore. But these graphs were probably generated by slide rule and points, and they've actually plotted on what's called graph paper. I don't know if you've ever heard of graph paper. Sometimes you can, maybe museums might have graph paper. So then they would give it to a graphics artist who would trace over this and come up with these vellum tracing, beautiful things. This is the way life used to be in science and technology. So I want to point something out here, and it took me a few years to realize this. Remember back here where the resonance and the anti-resonance are really close? Okay, so here we are, the heavy, stiff driver, right? First resonance there is, so here's the resonance. Where's the anti-resonance here? The key word is artist, graphics artists, okay? So the graphics artists, where should this be? Very close to here. This should drop way down and start to slowly come up. It should be it was drawn here as kind of symmetric. That's not right. That can't be right. No big deal, but I just wanted to point it out to you. Okay. So we've already talked about this. Anybody's interested, let me know. All right, does anybody have any questions? Okay, so tomorrow is the lecture for the experiment, for the acoustic modes of a cavity.